Hello, what is up? We are here with the Honors Physics number 5 on the second Forces and Free Body Diagrams problem set. In this question, we've got Scrooge Combs' big drill spin of pain technique. Those of you who were here for the last day before we went online may remember Scrooge Comb. Thank you for saving me from him, by the way, and his physics problems that he made for you guys. He had a technique called the big drill spin of pain, which launches a marble at a solid 0-degree angle. Basically, how this works is you have a drill, like so, a power drill. You have me. There's the drill bit. It is connected to a large piece of wood, and on the end of that is a cup that has a marble in it. So how this works is you pull the trigger, this thing spins around in a circle. Then when you let go of it, the marble, the centrifugal force keeps the marble in the cup the whole time, spinning around. Then when you let go of it, it drops and acts like a projectile. And in this problem, we're going to have to treat it like a projectile. So, we launch our thing at a solid 0-degree angle, flat horizontal line, launching a maximum distance of 3.4 meters from a starting height of 1.7 meters above the floor. So what we're saying is that this distance between here and here is 1.7. This distance between the edge of where it goes and where it lands is 3.4 meters. That's 1.7 meters. Okay, so we take our drill, spin it up horizontal, 1.7 meters above the floor, let go of it, it lands 3.4 down below. If we assume the marble behaves like a projectile after it leaves the edge of the cup, which we do, find the distance the cup is from the end of the drill, the radius of the circle, so we're looking for R. Assuming the marble is 0.045 kilograms, equals our mass, and it moves with an acceleration of 11 meters per second squared. That's our acceleration. Okay, so first things first, we're looking for radius. We want to know what our forces acting on this thing are. Well, we have a thing moving in a circle. Good news, thing moving in a circle means that it's centripetal force. So let's go to our problem sheet, take a look. FC for centripetal force is mv squared over r. So FC equals mv squared over r. Cool. So we also know that this is a force. Force is equal to mass times acceleration. Let's see if that helps. We're given an acceleration and a mass, so maybe it does. Let's take a look. So FC equals 0.045 times our velocity we don't have yet. R is what we're looking for, and that's equal to 0.045 times 11 meters per second squared, which is our acceleration. Now, this is a problem that you guys ran into when you were doing Scrooge Combs' thing, right? We don't have velocity, but we can get it by treating this like a projectile. We know that however fast it's moving around here is how fast it's moving as soon as it's let go, right? So we can find this velocity by treating it like a projectile. And in doing so, set ourselves up a little projectile problem over here. So we have initial and final position in x, initial and final velocity in x, and acceleration in x time. We have initial and final velocity in y, initial and final position in y, acceleration in y, and time. Okay, so our acceleration in x is 0 because it's a projectile, right? It's falling just because of gravity. Gravity does not act in the x direction, only in the y, so that's 9.8 for the y. I'm just going to call down positive and up here 0 for simplicity's sake. So yi is going to be 0. Yf is how far it falls. That's positive 1.7. Xi, 0, as we always call it. Xf is how far it falls over this way. That's 3.4. Vfs we don't care about because it's a projectile. Now, because this is moving horizontally, right, it's at a 0-degree angle, it is going to have no velocity in y, that's going to be 0, and it's going to have a velocity in x, which is v, which we're trying to find. Okay, so this is a projectile problem. We solve this for the side we have more information in, which is this half, and we plug it into our fourth kinematic equation. which is yf equals yi plus vi and y times t plus 1/2 a and y times t squared. Plug all of our stuff in here, solve this for t. We get 1.7 equals 0 plus 0 times t plus 1/2 9.8 times t squared. That's 1.7 equals, that's 0, they cancel out. 4.9 times t squared, divide by 4.9, divide by 4.9. (1.7) divided by 4.9 gives us 0.34. That's t. Take the square root of that to get, or sorry, that's t squared, excuse me. Take the square root of that. We get t equals 0.58 seconds. From this, we can go back over here and solve this for velocity the same way. So we use the same equation. I'm going to move it up here. So that's xf equals xi plus vixt plus 1/2 axt. Oh, geez, that was a mistake. Sorry about that. I'll do it again over here so it's easier to see. So that's xf equals xi plus vixt plus 1/2 axt squared. So now plug all of our stuff in here. Xf is 3.4 equals xi is 0 plus vix is v. T is what we just found. That's 0.58 seconds. And then 1/2 axt squared. Ax is 0, so that whole thing's going to go to 0. So we get 3.4 equals 0.58 v. Divide by 0.58. 3.4 divided by 0.58 gives us v equals 5.9 meters per second. So now that v is this v. So this v that we got over here, we can replace with 5.9. And now this is really easy. All we have to do is solve this for r. So doing so, we can, you know what, let me write this on a clean sheet of paper. Where did I put my clean sheet of paper? Here we go. So if you guys remember, we said mv squared over r. Our centripetal force is a force, so it's equal to mass times acceleration. So our mass was 0.045 kilograms. Our velocity we just calculated is 5.9. R is what we're trying to solve this for. Mass is the same mass, and acceleration is 11. So solving this for r, we can multiply both sides of this by r. Cancel, cancel. We get 0.045 times 5.9 squared equals 0.045 times 11 times r. So that's 0.495 r. So we can go ahead and solve this side too. That's exponents first. That's 5.9 squared times 0.045. 1.56. I'm going to call that 1.6. So that's 1.6 equals 0.495 r. Divide both sides by 0.495. We get 3.32. So that's 3.2. Or sorry, not 3.32, 3.23. So that's 3.2 meters is the distance. So that's how we solve that one. Not so bad. The only part that's hard about this is that you have to think through it a little bit. You know, you have to say, all right, this velocity I'm getting from it being a projectile, the speed that it's moving with around this circle is the same speed that it leaves with before it falls to the ground. So that's the idea. Hopefully you guys have found this one pretty easy. I'll see you guys in the next one.